Okay, in the last video, we derived an expression for the average case running time for the unique elements algorithm that was based on some assumptions. Right? In particular, it was based on this assumption that if we run this algorithm, it's very likely, so on a random input, it's very likely to return true. And where returning true corresponds to all the elements being distinct. So our analysis was based on that assumption. So if that assumption fails, our analysis is invalid, right? And so this is one of the deep challenges with average case running time, is that it ends up being highly contextual. Okay, so our first assumption is that the set of possible array elements was huge, right? Was essentially much, much larger than the expected length of the array. So what if that's not the case? So what if we make this assumption? And I'm not going to try to justify that this assumption matches an application, right? But let's just make an assumption and do what we do in CS theory and chase the assumption down and find out what its consequences are, and then see what we can learn based on this the consequences that we find. So here's our assumption number 2. Rather than the number of possible array elements being large, what if for an array of size n, we have a library or an alphabet of exactly n values that the array could take? Okay, so what if an array contains only n possible values? Only n possible values for length n array, right? And like I said, I'm not going to try to justify that this is a reasonable assumption, but let's try to see if this changes anything. And the first question we'll ask, and this is the only one that we'll answer rigorously, but the question is, what is the probability that based on this assumption, right? If our inputs are generated by this assumption, what's the probability that the algorithm returns true? So what is the probability that UE of A is true under that assumption? All right, well, first of all, we need to characterize the possible input space here, right? So first question, so this is Q, here's Q1, here's Q1A, right? Q1A is how many possible inputs there are there, right? So what we'll do is we'll figure out how many possible inputs are there. We'll figure out how many of those inputs return true, and then we can figure out the proportion or the probability of inputs that cause the function to evaluate true. So the first question is how many inputs as a function now of n? All right, so the answer to this is kind of shockingly simple. It's n to the n, right? So now I can say that. You can say, oh, he's a professor, he probably knows what he's talking about, and just believe me. But with this kind of thing, it's useful to train yourself to derive these things from scratch if you need to, because sometimes it's helpful to know kind of how big numbers you're thinking about. So let's think about why it's n to the n. Well, first of all, what if n is 2? Let's just actually work this out for n equaling 2. Well, then there's, you can think of this as the number of binary numbers that have 2 bits, right? So then the question is, how many binary numbers can you make with 2 bits? Well, you can make 4, right? That's something that you should be able to do in your head. If you can't do that in your head, go read everything you can read about what binary means, right? This is important. Okay, how many binary numbers can you make with 2 bits? You can make 4, and there they are. I just wrote them out. All right, so what about n equals 3? What are we talking about with n equals 3? So what we're saying is we're going to build an array of length 3, right? Build an array of length 3, and then we're going to have an alphabet of 3 symbols that we can choose from. Okay, so let's just follow the same analogy that we used with n equals 2 and say this is the number of 3 trit ternary numbers. Okay, so this is 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 2, 0, and so on, right? So n equals 3. This is the number of 3 trit, right? A trit is a ternary bit, right? It's a 3-valued digit. Number of 3 trit ternary numbers. Right? How many of these are there? Well, we have 3 possible things that can go here, 3 possible things that can go here, and 3 possible things that can go here. And if you multiply all this out, you end up with 3 to the third. Right? And you can kind of justify this to yourself by saying, well, rather than saying how many 3 trit ternary numbers there are, let's just think about how many 1 trit ternary numbers there are. Well, there's only 3, right? If I add another trit, then I have 3 more possibilities for each of those spots there, so I end up with 3 squared. If I add a third trit, I end up with 3 cubed, right? And I can chase this on, and if you think about it in terms of decimal numbers, that may help you as well. How many 10-digit decimal numbers are there? That's exactly 10 to the 10. Okay, so there are n to the n inputs, and with combinatoric problems like this, it's very useful to be able to say, the number of arrays that I can make with n of length n arrays I can make with n symbols has to be exactly equal to the number of n-digit numbers I can make in an n-array number system, okay, or a base n number system. So there's Q1A. We have n to the n possible inputs. Now, how many of these inputs return true? So Q1B, how many return true? Well, here, the answer ends up being also a massively large number, but it's a smaller number. The number that returned true is n factorial. Okay, so another piece of information, combinatoric problem-solving information that you should memorize is that if you have an array, the number of permutations of that array is n factorial. Okay, so the number of different ways you can reorganize that array without changing any of the actual symbols is n factorial. So why is n factorial the answer here? Well, the question is, suppose I have exactly n symbols, and I lay them out all together, and there are no repetitions, right? And I have n slots to put them in. Then any way of arranging those that has no repetitions is a permutation of my original array. Okay, and so this is if it is unique, if all the elements in this array are unique, we know there's only n symbols, we know there's only n array slots, so that means it must be a permutation of just the list of all n possible symbols. Okay, so how many return true n factorial? Because then this is just the number of permutations of n elements. Okay, so that's how I derived that one. And again, we'll do this several times throughout the semester, but it's very useful to be able to sit down and look at a combinatorics problem and say, I can connect this to something I know, and then solve it. Okay, so now our original question. What's our original question is, what is the probability that if I feed an array that has statistics according to what I've described, that I feed that array into this algorithm and it returns true? Well, it's just the number of arrays that return true divided by the number of arrays. So back to question 1, right? The probability that UE of A is true, right? This is this is a number, this probability is a number, right? This is equal to the number of true inputs. I'm being a little bit flippant here, a little bit informal, but this is correct. The number of true inputs divided by the number of possible inputs, and this just equals n factorial divided by n to the n. Okay, so now we've not done this one yet, but we actually know we have the machinery to understand what this probability is when n is large, right? So I can say, what is the limit as n approaches infinity of n factorial over n to the n? And I know Stirling's formula, right, which helps me understand what n factorial looks like in the limit. So this is equal to the limit as n approaches infinity of, again, we'll do this fraction, and Stirling's formula, I have to look it up because I don't have it memorized. Whether you memorize it is up to you. So it's the square root of 2 pi n times n divided by e, the natural log base, to the nth power, now divided by n to the n. Okay, what does this do when I chase it through? And so this is all the same probability. Remember, I'm calculating the probability that my algorithm returns true in the large n limit. So this equals the limit as n approaches infinity of 2 pi n times n to the n times 1 over e. Here, actually, I'm going to rewrite this just a little bit, and I'm going to put that on the bottom. N to the n over e to the n times n to the n. Right? My n to the n's cancel, and I end up with 2 pi n divided by e to the n. If you would like to do the math and work out exactly why this thing goes to 0, you may, but I hope that it's clear that this thing gets very, very large, right? That e to the n is a huge, it grows exponentially fast, and we're dividing by that. So it's going to grow much, much faster than the square root of n. And so this ultimately gives us that the limit evaluates to 0. Okay. So recall, in our previous analysis, where we assumed that the space of all that, or that the number of symbols that could show up is huge compared to the length of the arrays, we said that seems to imply that the probability of returning true is greater than 0, right? And potentially we made the assumption that it's independent of n. So our old assumption is that PU is greater than 0 and independent of n. However, if we modify our assumptions a little bit, this may fail. And in fact, it may be that we can say that in the large n limit, if we have this strange limitation on what symbols we can put into our array, in the large n limit, the probability of returning true may actually go to 0, right? So in our new assumption, we have something different that comes out. We have that the limit of PU of n as n approaches infinity equals 0, right? Which will affect our analysis. So I'm not going to chase the rest of the average case analysis for this algorithm. Feel free to do so. It can be quite complicated because this isn't the only case that gives us a quadratic running time. However, the point of this is by modifying our assumptions about the statistics of the inputs, we end up with completely different conclusions about what the average case running time is. So this essentially is the core of the reason why we focus on worst case in this class, right? Is that average case is immediately messy, right? As soon as you start asking average case questions and then trying to derive anything, everything you do is extremely sensitive to your assumptions, extremely sensitive to the statistics, and it's not clear that the answers you get are going to be predictive of what you actually would see in the real world. So this is all a cautionary tale with mixed cases. I'm not sure how that worked there, but as you move forward, if you see average case, it's helpful, it's meaningful, but it's really good to understand where it can come from and where it can go wrong.